interactions. Okay. Problem? Acha, okay. So, but before I do that, do you have any questions from yesterday? If you have any question, you can quickly ask me, else I'll just start. So I'm starting. Huh? So, as I said, we will do interacting scalar field theory, and this is my interaction term. Why I am calling this interaction term? I'm calling this interaction because if you look at it, it involves 4 phi fields. So the part of the action which is here, which is in the free kg theory, if you remember, this action, this part only had 2 scalar fields. Right? It has a term which was you knew del nu phi, so 2 phi's, and then m square phi square. So whenever you will find the equation of motion from this kg piece, you will always get an equation of this sort, some operator plus some constant or some functions acting on phi equal to 0. So it will just give you a linear equation. So there I see some chat message. Give me a minute. Okay, we can talk about it later. Okay, I have started interacting theory. We can talk about it later, or we can discuss this in the tutorial. Let me, since I have already started interacting theory, let me go ahead with it. Okay, so as I was saying, so any term when you are adding to the action, if it contains more than 2 fields, okay, we will always think of it as an interaction term. And in that way of defining interaction, you can clearly see that this term would be an interaction term. And I gave this as an exercise yesterday, that if you add this piece to your Klein-Gordon, usual Klein-Gordon action, then the Hamiltonian will turn out to be whatever I have written below. And the most important relation that you can check, I asked you to check it. I don't know if you have done it or not, but you should do it. You can check that if you write everything in terms of A and A dagger and all, then H with N is not going to be 0. Which means that now your number operator is going to time evolve. It is not going to remain same over time. So this equation readily implies ddt of n is not 0, and hence number of particles will change with time. Okay, that is exactly what we really wanted to do in our quantum formulation. We wanted to understand a system where multiple relativistic particles will can get into some sort of change, such that after the change we might get more particles or less particles. Okay, and all we are trying to say is, we were trying to find a mathematical formulation for that. We saw that quantum field theory is good enough to describe a continuum of relativistic particle, but if I do not add the interaction term to it, then I cannot change the number of particles. Right? H with n was always 0 for any free theory. We have already done in the class just scalar field theory, but this is a feature that is true for any other field theory. I will at least talk about one more field theory during these lectures, but whatever field theory, free field theory you can write, for all of them this is true. So we certainly need more than free field theory, and that is what we are going to learn now. Okay, so that's it. This is the interaction term that we are going to study. This is just an example, but via this example, we will learn the techniques, we'll learn the procedure, and that would be applicable for any other interacting field theory. Okay. Now, you see, one thing that you can readily, very quickly do, all of you, is just try to find the equation of motion for this system. You already know that from the Klein-Gordon piece, the equation of motion that you get is this, like box plus m square phi equal to 0 was our equation of motion. But now, since my action has another extra piece, which is this phi to the power 4 piece, that will also contribute to Euler-Lagrange equation, and hence your Euler-Lagrange equation will now change to this piece. And now you already see that the system, even for such a simple interaction, is non-trivial, right? Because it's a second order differential equation. It's a second order partial differential equation, which is non-linear. And in general, it may not have a defined solution at all. So if you want to find, the first term goes with phi and the second term is with phi cube, right? So it's not a linear equation. If you scale phi by some number, say a or b, the first term is going to scale as a, whereas the second term is going to scale as a cube, right? So it's a very difficult, different kind of a equation, and in general, it's very hard to solve such an equation. One cannot solve it for any value of lambda. Rather, one has to use certain techniques to solve it, and we will see how to handle this system. But all I wanted to say is that you can already understand that the system is going to be pretty dirty. I mean, it's difficult. It's not exactly how it was. And that this statement is even more evident if you think of what we did for our scalar field theory. We defined things in the momentum space, right? You remember? And in the momentum, I cannot show you that file today because this is a new file for me. Okay, I'm just starting a new folder. Actually, I realized while giving you people these lectures that quantum field theory, it's very hard to teach on an iPad because quantum field theory really requires 2-3 big boards. Anyway, yeah, that is beyond our scope, but let's just try to understand. So you remember that the Klein-Gordon equation in momentum space was basically just boiling down to the harmonic oscillator equation, right? And it was because of that harmonic oscillator that we could define the creation and annihilation operators in the usual sense of harmonic oscillator creation and annihilation, and can do the entire calculation very easily. Right? We could really construct the Fock space. We could construct the single particle state, two particle states, really checked that that single particle states was describing a relativistic particle of energy E and momentum P. All those nice features that was there in free theory is no more going to be true anymore. Right? Because now in the momentum space, the equation will not be harmonic oscillator. So yes, you can introduce a dagger and an A operator, but their meaning would be very different than what it was for harmonic oscillator because their time evolution is going to be different. So these are the complications that are going to come. Nevertheless, it is still a quantum theory. I will still have a Fock space. Well, yes, the Fock space doesn't have nice interpretation anymore. But okay, if I want to build upon a prescription where the particle number is not conserved, then to gain something, we have to lose something. And here, to gain the particle number non-conservation, it seems we have to lose the nice physical interpretations that we had in free theory. Okay, for example, the particle-like interpretation is no more true. It would be even more evident as I will go ahead. Okay, fine. So let's see, even with this, how much we can learn. So I will still have a Fock space, right? And the Fock space I'll define like the last time, with starting with some vacuum states, where now the definition of the vacuum is simply that H acting on the Hamiltonian or the energy operator acting on the vacuum is going to give me the lowest possible energy states of that system. Every other state will have energy greater than T0. T0 can be 0 also, but whatever it is, there would be a lowest energy state, and that is what I'm going to call my vacuum. Okay. So with this much, let us see what can I do. So you remember that so far what we really found was interesting was this object, the endpoint function, right? Some time ordered product of some bunch of operators, something I only did in the class 2-point function, but in principle, I can have some time order product of some bunch of operators acting on the free vacuum, and we could find what this quantity is, right? This is what we called was an endpoint function, Gn. Okay, but in free theory. So I'm going to put a F here just to denote that these guys are free vacuum and these guys are free theory operator. And this is free vacuum. This computation we have done. Particularly the 2-point function we have done very clearly. In fact, more than that, I gave you some exercises. And if you have done that, so you can understand that in principle, one can go ahead and do such calculations, write the result in terms of Feynman propagators. One can integrate also if one intends to, or at least diagrammatically one can understand. Okay, so this is what we did. But now, so this, I should not say goal, we are now doing, we did this. Right? Now our goal is going to be to find the same quantity, but in our new theory, which is the interacting theory. Phi x1 to phi xn. Okay. And let me call it G, now proper G, x1 to x. Writing capital, let me make it small. Okay, this is what we call is an n-point correlation function. Most important and interesting object in any quantum field theory. Correlation function in the QFT. This is what we still want to find. But now with a pinch of salt. What is it? Now this guy is not this. Okay. And these guys are also not the free field, free theory XT. Okay. But nevertheless, this is a state and this is an operator. Okay. So this quantity makes perfect sense. As a definition, this quantity makes perfect sense. I have a theory. In that theory, I have a lowest energy state, that is omega. Now I am computing the expectation value of some number of time ordered operator of my theory with respect to this lowest energy state. In a quantum field theory, in a quantum theory, this is an absolutely well-defined quantity. The problem is we do not have the machinery to do it. Right? Why? Because neither we understand these operators. Because all those A daggers, A acting on 0 is 0, A dagger acting on the state, is a new state. All those are gone. So neither I understand this, nor we understand this state. What is this? Only definition of omega that I have is that omega is the energy state of my theory. But that's it. Nothing more than that we know. And then I do not have an idea how am I going to compute this quantity. Okay, so that's the goal. We have to compute it somehow with whatever machineries we have built. And what machinery have we built? Okay, so let me first make a sub-goal. Sub-goal is, let's first just try to compute a 2-point function. Okay, 2-point function by definition would be T, time ordered, phi x, phi y, omega. Okay. In my theory, let us first compute the 2-point function. We know that in the free theory, this 2-point function is nothing but our Feynman propagator. We know its integral representation. We know its diagrammatic representation. Okay. If you want to compute, you have to find the integral. If you just want to understand what it is from writing down the diagram, that is even more easy. Right? Feynman diagrams one can do. When Feynman diagram means integral is the computational tool, and Feynman diagram is more like an expressive tool. This we knew. But with this, so with the known machinery. Now, what do I mean by that? By that I mean I just know this. I know this, I understand this state. With this information, can I go ahead? That is my goal. That is what we have to do. Can I find this quantity? Okay. And what we will show in today's class is not just this quantity, every such quantity can actually be obtained. Okay, with some ifs and buts that I will keep on adding as I proceed. But is it clear? Is our goal clear? If any of you have any doubt, you can ask, else I'll proceed. Okay. So this is our goal. It is, we all understand that it is non-trivial. We all understand that it is absolutely necessary for us to find it. So let's go ahead and find it. Sure. So when we know that something is not so trivial or something is difficult, you all will probably be doing research. The best, I mean, the most important part is to analyze the difficulty, is to understand where it is difficult, why it is difficult. Only when you understand the difficulty, you can try to solve the difficulty. So let us break this and try to understand exactly what is going wrong. I mean, by wrong, I mean what is not going as we understood it before. What is different here? Very explicitly. Let us go slow to understand that. So let's start. So let me write down H as I have already written down as H free plus H interaction. H free is good guy, we understand it. HF is also a good guy, but we don't understand it. So we'll see how to deal with it. Now consider some reference time, some time, whatever, T naught, and write a field at that particular time T. So this quantity, whatever it is, must be a function of x only, because I have already fixed the time, so it cannot depend on time. And if I want to write it in the momentum space, by now we all know that we can write it as some d cube k or p 1 over square root 2 omega k a k a k t0 exponential of I k dot x plus some a daggered k t0 exponential of minus I k dot x. Okay, this is just notational, but first level of difficulties. But now this is true. D dt of a k t simply I full H comma a k t. And this H is HF plus HI. Okay. So this is different from free theory. Okay, clear? Because in free theory, this was only HF, and we already knew that HF with A equal to minus I times E times A, EK times A, or omega K times A. Now you don't know that, because the result is going to depend on what is your HI, and of course, depending on different HIs, the result is going to be different. So although this expression looks very similar, okay, to whatever we have, but these guys that are sitting here are not so trivial, because they now satisfy this equation, which is pretty non-trivial. So we understand our first subtle point. Okay, good. So it is whatever it is, and let's proceed. So now, okay, now, nevertheless, we are trying to understand that how an operator is going to be a function of time. Here I have defined an operator for you, which is at a fixed time t naught. But now if I ask you, okay, but what would be this operator at any time t? You know that in the Heisenberg picture, I just have to time evolve it with respect to the full energy operator of my theory. And now I have explicitly kept that t naught. Earlier in the class, I was doing it for t naught equal to 0. Now I have just kept it. Okay. So again, this is the second subtle point, and the subtle point that now your H is both HF plus HI. Okay. Again, this expression is very easy to write, right? But finding the right hand side is not that easy, because what I have is not just the free H, but the full H. Okay, so this is our second point. But so far, I'm just telling you about the subtleties. So if I just stop at this line, I really cannot do anything, right? Because I don't know. It completely depends on what is my HI. Otherwise, I cannot. Otherwise, I have no hold on this equation. And of course, I'm sure you would agree that we do not want to write theories for every interacting Hamiltonian. Right? We just want to build up a prescription which would be valid for no matter what is my interaction. So there is not really any point to try to solve this equation for our system, because that's not what we are trying to do. Next day, somebody else will give you 5-6 interaction or 5-cube interaction or whatever interaction. Then again, you have to go back and hope to solve this equation. That's not what we are trying to do. Okay? Just a sec. There is a question. Pre-theory we used P and EP. Is there a reason we shifted to? No. You can still call it P and EP. This omega K is exactly same as EK. Yeah, it's no reason. It's just a different. I am just using a notation. Why K dot X and not KX? Because they are vectors, no? And this I'm writing just for the 3 vector dot product. So it becomes the 4 vector dot product when we take out the T dependence from A and A dagger. That you could do for very easily for your free theory. Now you cannot do it. So now it's really 3 vector product and not the 4 vector product. Okay. Fine. So, okay. Now what can I, at this step, what can I do? Is there, do I have any hold on this system? Okay. So yes, we do have some hold on this system, and that is this. Please pay attention. In the limit lambda goes to 0, H is just H free. HF, right? By HF, I mean H free. Agreed? Recall. This is H. H had this piece, H free plus H interaction. And your H interaction was explicitly dependent on lambda. If I take this lambda to going to 0 limit, then whatever I am doing should just simply boil down to free theory. You have a question, Arinda? Yes, ask.
Please go to the previous page and per goal, second goal, write 0 state.
Goal.
Ma'am, why, ma'am? We used Fox space in vacuum lambda state. Why not 0 state? Means in previous class we solved from 0 state, but here the lambda state. Why use the lambda state instead of 0 state?
Okay, it is so. Okay, good. So I should probably explain it a bit more. This is a notation, which means the definition is in the free theory, this is free Hamiltonian, acting on 0 was 0. Okay? We checked it explicitly. Do you remember, right? In our Klein-Gordon theory, we saw that the vacuum has 0 energy. Now, your theory has changed. Your theory does not have HF as the energy operator. The energy operator is H. So you can definitely take H and act on 0. It would be something. It would be something, some state. But I want to define the Fox space with respect to a state which has this property. Some E naught times omega, this E naught can be 0 also, but such that for every other state, H on N equal to maybe for every other energy eigenstate, some En times N, such that En is always greater than E naught. If you go back to your free theory, that omega is nothing but the zero, because zero has the lowest energy. It's just a notation to tell you that we are in a different theory where the two vacuums need not be same, no? Because you agree, right? That
Yes,
the
ma'am.
vacuum of free cannot be the vacuum of your interacting theory, because your interacting theory energy operator has changed. So now I'm writing down, I'm starting from that state and denoting, again a notation, denoting it by omega, but it also has exactly the same property as the zero of free theory. The zero of free theory was the lowest energy state of free theory. The omega of interacting theory is the lowest energy state of the interacting theory. And they are
So
not
this
same.
is happening. So this is happening because of the 5-4 we have written in the Hamiltonian.
Exactly. Because we have, this is happening simply because we have a different theory, right? Now we are studying this theory. We are studying this theory, na? Initially, we were just studying kg. Now we are studying a different theory. You have changed your theory. Okay, I have changed it in a very smart way that as soon as I take lambda goes to 0, I go back to my old theory. True. But nevertheless, in presence of lambda, the theory has changed. Okay? Clear?
Okay.
Okay. So, let's go ahead. So now again, recall that if even in your theory, the theory which is not kg but phi 4, kg plus phi 4, if I take lambda goes to 0, my Hamiltonian, the energy operator would simply just be H free, because Hi is proportional to lambda and that piece would be 0. So therefore, any operator in your theory, by that I mean in the part of, I mean in the theory in presence of phi 4 interaction, as soon as you take lambda goes to 0, there I can replace this H by H free. Right? Because in the lambda goes to 0, H is free. And the only operator that is appearing in this expression is H. So I can just replace it. And let me define it by phi I of xt. Okay, so this is an operator that is defined in terms of free theory objects, but it is from the interacting theory. This phi I is an operator of your interacting theory in the limit lambda goes to 0. The left hand side, the phi, is an operator of your interacting theory. That operator in the limit lambda goes to 0 can be expressed in terms of quantities that are very well defined in the field theory. That we understand. The right hand side phi I we understand. We can express it. So in terms of known quantities, I have expressed my operator of the interacting theory, but of course in the limit lambda goes to 0, not in a generic lambda value. ठीक है? You might think इसमें बड़ी बात क्या है? Of course, in the left hand side also you are taking lambda goes to 0. So effectively you are going free. Yes, correct. Correct, I am going free. But nevertheless, a full operator, phi, it's an operator of the interacting theory. I can do calculations with that operator and then eventually take lambda goes to 0 limit. When I will take lambda goes to 0 limit, at that point I can replace the phi operator by phi I operator. ठीक है? Okay? Good. So phi I is good object. It's a good guy and I understand it completely. And the big part is that even my operator that I don't understand at all, in certain limits have this nice interpretation. Great. Good. So then what? Okay. okay. Also recall that in free theory, I mean, this you all know, but I'm just writing. Exponential, if in case you do not know, I'll ask you to just do the calculation. It's very easy. It simply comes from its equation of motion in free theory. Minus I H naught, H free. I am writing H free, I'm sorry. T minus T naught equal to A exponential of minus I omega k or EK, whatever you want to use, T minus T naught. And similarly, parallelly for A dagger. Okay, so I'm saying that A and A dagger of free theory, we know how the timing. So therefore, this guy, phi I x t, I can just write in terms of known quantities. This is what I meant. When I said that I know it, I understand it. What I meant really is this, that I know it in terms of a akt exponential of minus I k dot x plus, sorry, acha, okay. Now I'll do what you wanted me to do. You wanted me to write it in 4 vector notation, right? So it's like ak0 exponential of minus I k mu x mu plus A dagger k0 e power of I k mu x mu. This I know where and where. The best part is these guys are, this A and A are things are free theory creation annihilation operator. By that I mean AK on 0 is 0, AK dagger on 0 is some state up to that factor of 2 omega k, square root 2 omega k probably. Okay, this we know. So that's what I mean that I understand phi I. Okay, although this phi I has this nice, it is an operator which has interpretation in both theories. I know it completely in terms of free theory objects, but it is also the operator of my interest, of my theory in the limit lambda goes to 0. Okay, good, fine. Now, if I know this, the question is, what is then phi xt? See, now I am moving away from lambda goes to 0 in terms of phi it, right? If we know this, then we are done. So far I know, what do I know? I know that this phi xt, I know that this phi I xt is nothing but phi xt, but in the limit lambda goes to 0. But that's not what would really satisfy me. If I want to compute, if I want to reach to my goal or to my sub goal, I really need to know phi xt, not in the limit lambda goes to 0. So then what I really have to find is this quantity, right? What would be this operator in terms of the operator that I know? Can I find it? If I can find it, then brilliant. Then I have something really non-trivial. Okay, let's see if I can find it or not. So you agree this to this point, right? That phi xt is an operator at any time t would be exponential of I h full h t minus t naught phi x t naught into exponential of minus I h t minus t naught full h. If I know the operator at any reference time t naught, then I will just evolve it as per the Heisenberg picture and I'll get the operator at any time t. That's what I have written. So you all agree with this relation. And now recall something interesting. You recall this. Now you recall this entire expression. This which was equated to phi I. Okay? Okay? If this is so, then I can write phi xt naught in terms of phi I xt. Okay? Let me do that. So this expression is same as exponential of minus IH T minus T naught exponential of, sorry, this was plus, I'm sorry, minus IH free T minus T naught phi IXT exponential of IH free T minus T naught into exponential of minus IH T minus T naught. Lovely. We are done. Or what have I done? All I have done is I have used this relation. I have multiplied the lower line with respect to exponential of minus IH naught from left and plus IHF from right. I have multiplied phi IXT by exponential of minus IHF from the left and plus IHF from the right. Effectively, in the above line, the two exponential factors from both sides are cancelling and you are getting phi XT naught. Lovely. So as soon as you have that, now you see what I have obtained. I have obtained phi XT in terms of phi IXT. Right? So I can write this now as some U dagger. Let me write, I'll define it for you. T phi IXT U T. What is U? U is nothing, U dagger is nothing but this quantity and U is nothing but that quantity. So let me just define it for you, where U T is this operator, exponential of I H naught T minus T naught times exponential of minus I H T minus T. Okay? So, in your theory, in the interacting theory, the operator is time evolving with respect to a free theory operator via this object U. Okay, this is not, U is not just exponential of I times Hamiltonian times time. That's not what it is. U is product of two operators where H naught, okay, I'm sorry. I am writing HF. Sometime I just write it as H free, where H, U contains both the energy operator HF as well as H. But if I know this, if I can understand this time evolution operator better, then that is what will give me an operator in my theory, in my interacting theory, phi xt, from the information of an operator in the free theory, which is phi ixt. Okay, good. So then our next job is, to get ut in a suitable form. So again, to do that, all I need to know is what is the equation of ut. So ut will satisfy this equation. So from this is definition. From this definition, you can check that this is true. I del t of ut equal to h I t ut. Okay, where by h I t I mean this. This is the operator. HIT is exponential of minus I HF T minus T naught times H. Okay, I think you will get, let me call it INT, interaction. Okay, H interaction at T naught times exponential of minus I H free T minus T naught. Okay. So here, this line will lead to this line. You just have to take a derivative and you will see that this is what you are getting. Okay. So this, once I have it with an HIT here, where HIT by definition is this quantity, I know the equation of U. Okay. Let me give this equation a number. This is a very important equation. Let me box it. Bad color. Let me call this equation 2 and this equation 1. This equation 5x. So if I can solve 2, so if we can solve 2 and put back the solution in 1, we know this operator. The operator of my interacting theory, I would know it completely. So then my immediate goal is to solve 2. Now you see, look at 2. 2 is a differential equation. First order differential equation. If I have to solve a first order differential, yes, it is a unitary transform, yes. If I have to solve a first order differential equation, then what do I need? I need one boundary condition. You check that just from the definition of U. Check. I mean, there is nothing to check. It's just so easy. What is UT not? Tell me. You guys can't sleep in my class. Tell me, what is it? One, not one. Identity, right? Okay, so this is the boundary condition. So this is the boundary condition. So then my job is solve 2 with boundary condition UT not equal to identity. And if I am successful in doing that, then I'm successful in I'm successful in understanding an operator in the interacting theory with some known quantity. Good. So now what I'm going to do, in my usual class, I would have done this solution for you. But in this class, that would be too much. So what I'm going to do is I'm just going to give you the solution. And then I'm going to provide you notes where I have the details derivation of the solution. Okay. So here I'm just going to write the solution is following. If you have done perturbation theory, then you must have done it already. I mean, in quantum mechanics, if you have done perturbation theory for time-dependent system, then you know this already. But in case if you have not done it, then you may not know it. That's okay. Don't worry. For today's class, the derivation is not important. But of course, for understanding, derivation is important. And we can do that at some other point. You can do that at some other point. I'll provide you with my notes, which is very detailed. Okay. So this is what the solution comes out to be. It's a time-ordered product of this exponential operator that only depends on HIT. And what is HIT? Let me remind you. HIT is this quantity. I have defined it right here. This is HIT. In fact, if you just rewrite things properly, you will see that HIT would be this operator, lambda by factorial 4 d cube x phi I for our theory. This is just phi I to the power 4 xt for us, for our theory. Of course, for a different interacting theory, you have to, this HIT is nothing but d cube x. Okay, there is no d cube x. Also, HIT is nothing but in H interaction, you just replace phi by phi I. That is what is HIT. Okay, again an operator that you know. I don't know H interaction, right? Because H interaction is this expression with phi to the power 4. And phi is an operator that I do not know. I am trying to understand it. But HI is not that. HI is exactly that expression, but phi replaced by phi I. And phi I we know. Okay, so that's your HIT. And hence, you see, now you also know your UT completely in terms of objects that you are familiar with, right? Because it involves HIT. You understand phi I operator. Okay. Okay. So I know you. If I know you, then I go back. I put it back here in this expression. I know it, all my files. All operators I know. Okay. Let me remind you my sub goal again. My sub goal was to find this expression. This expression. Okay. I have been successful so far in understanding this object. I know. So now, after these 2-3 pages, now we know. By know, I mean we understand. By understand, I mean we can compute in terms of free theory objects. That's what I mean by we know this quantity. The operator we have understood. Okay. So now to reach to my goal, but what was my goal? My sub goal was this guy, right? Phi time ordered of phi x. I'm not writing t again. Here x is like 4 vector. This. So this was my sub goal. इतना मिल गया है. अब क्या करना है? So next job is to understand. Again, in my way of defining understanding, omega. Right? Because I know. So when I say I know, I basically mean I can express this phi x again in terms of some a and a dagger of my free theory. But a and a dagger ki, when I'm expressing in terms of a and a dagger, that is only useful if these guys act on 0, right? Some bunch of a dagger. If they're acting on 0, then it is useful. They do not know this guy. They don't understand what would be the action, what would be their action on this state omega. Okay? So I'm still not done. If I want to do the calculation, just understanding the operators are not enough. I also have to understand this state. And that's what we will do in the remaining time. I hope it's clear, right? So the question is, so next job is to understand this. Good. So let me do that. So a bit of an algebra, sorry, but this much I have to do because it has interesting physics also. Let's take this operator and act it on 0. 0, really the vacuum of my free theory. So this operator, this is the full energy operator. T is any time, T naught is the same reference time that we are talking so far. Let me introduce an identity. The identity that I am introducing is in terms of all the energy eigenstates of my interacting theory. Okay, so these are complete basis of energy eigenstates of full theory of H, not just H free. Okay, these are those states. Now this expression, I will have one state here that would be the vacuum for which the energy eigenvalue I know, E naught. And then every other state n prime, which is not 0, which is not vacuum, minus I En T minus T naught, every other state. And I'm just doing simple quantum mechanics. Okay, what is the speciality here? We have to remember that every En prime is greater than E0. Okay, fine. This is true. Now I'm going to do something very mathematical, but which is so rich in physics. First, let me do mathematics, then I'll tell you the physics. Okay? Take this T, you first make it slightly imaginary. Okay, the time, I'm just shifting it. I'm giving it a small imaginary part, and then first you make it imaginary and then take this t going to infinity limit. This is mathematics. What is really I am doing physically? Making time slightly imaginary and then going to future, far future. I'm taking t to infinity, positive infinity. So I'm going to far future. Okay. Now what would that do in this expression? This is very bad. I have to change this slide. So please write these two lines in your notes very quickly. Otherwise you will not understand. Okay. Even before let me try to do something here. See, notice that. Okay. So just concentrate on this term and this term. Okay. Just keep in your mind these two expressions. Everything else you can forget for the time being because I have to change slide. Now let me go. So what I'm doing is I'm taking, so one expression is exponential of I E naught t into 1 minus I epsilon plus t naught. This is one expression. Another expression is En t into 1 minus I epsilon plus t. Okay. This is going to give me some bunch of imaginary part, but one real part, and that is minus minus plus, I square is minus 1. This times E naught times T times epsilon plus some imaginary part I'm not writing. This, on the other hand, is going to give me minus En T times epsilon plus some bunch of imaginary. Okay. Now we what, and keep in mind that these guys are actually in the exponential. Okay. Now take t goes to infinity limit. You tell me which one will survive. Which one will go to 0 first? Tell me.
The real part.
Huh? Which one?
ENT epsilon.
ENT part, exactly. So in this limit, exponential of minus ENT epsilon will go to 0 much faster than exponential of minus E naught T epsilon. Why? Simply because E naught is small, no? Is smaller. It's the smallest one in En. So this is like exponential of 100 T epsilon. The first one is exponential of 10 T epsilon with a minus sign. So of course that will fall off. This one will fall off much faster. So therefore, after taking the limit, now I can say this, that limit t going to infinity exponential of minus I h t into 1 minus I epsilon plus t naught times 0 is just exponential of minus I E0 limit t going to infinity t into 1 minus I epsilon plus t naught omega 0. Okay, plus subdominant term. That we can forget about. Okay, lovely. Do you see what I'm going to get from here? You see, this is a number. Okay, this is also some number. Okay, of course, on the left hand side, this is an operator. Full H. Okay, yes, still a problem because it's full H. And this is our well-known state. So now I can just write this, right? So therefore, omega. Let me write it and you see if you agree. Equal to this left-hand side by a number. limit t goes to infinity, exponential of minus I E naught, t into 1 minus I epsilon plus t naught into this number omega times 0. Yes, you might see it a bit of alarming because I'm defining omega in terms of omega. True, correct. If that's your worry, it is valid, but nevertheless, as an expression, this is valid. Agreed? Okay. Now, what can I write it a bit better? Yes, you can. So let me write it. This is nothing but limit with all the definitions that we have given. It is going to be A inverse, where A is this quantity. This entire quantity is what I'm calling A. Okay. Times U dagger. This is the beauty. Okay, I have not done it, but if you put back all the definitions, you can see it in 1 minute. Comma T naught. Okay. So if you just have to put back the definition of U, you will see that the left hand side operator you can write in terms of U. And please remember that U is an operator that you have understood well. You have solved for U, right? That's what we have done in the last page. U I know. U I know. So all I have to find is U at a different time, which is this, at minus t times 1 minus I epsilon. Notice that here this t now is getting a minus sign. Okay, so what is it telling me? It is telling me that I need to take this time evolution operator now at far past, because t is going to infinity and there is a minus t, right? Far past. I have to take this time evolution operator at far past and operate it on the vacuum of a free theory. If I do that, then what I get would be the vacuum up to this number A inverse would be the vacuum of your interacting theory. Now, this is really beauty. Sorry, I cannot stop myself from writing this. This is beauty. So I now know the operator in terms of known object. I now know the state in terms of known object. My life is cool. Let me just write the final expression. Okay. Of course, I don't have to tell you that this guy would just be the corresponding bar state. Okay. So with all this put together, again, I'm going to suppress some 10 lines of algebra, but please allow me, otherwise we cannot do anything in these lectures. Omega t phi x phi y omega. I'm just dividing it by unity. These are all unit normalized. And I'm sure if you think a bit, it would be clear to you why I have done that. The expression will finally just be this. Just put back now. All that information that we have obtained, put it back and you will get this. 0 time ordered of. This time ordering is very important, and that is where those 10 lines of algebra comes. Unfortunately, I do not have time to do that. Exponential of minus I dt HIT 0. I will write the limits. This is from minus t 1 minus I epsilon to t 1 minus I epsilon. So I have to integrate this interaction from far past to far future. That, and in the denominator you have exactly the same expression without these 5s. So it's exponential of minus I dt HIT sandwiched between free vacuum from minus T1 minus I epsilon to T1 minus I epsilon. Okay, that's it. You see, I have absolutely achieved my goal. I know this, I know this, I know this, I know HIT is nothing but an operator written in terms of phi IT. So I know this, I know my entire numerator, and I know my entire denominator. Now comes that ifs and buts. Okay, but I gave you the solution of U, right? This was the solution of U. This was the solution of U, but this is not always true. you can only find this solution of u. So this solution, have I given it or not? Let me call this equation A. This very important equation. And let me call this equation B. Okay, so the important point is A, that is the solution of the u operator is only valid if we treat each interaction perturbatively in lambda. So this solution is only valid if I can think of lambda as a very, very small parameter that I can always take to the zero limit. So it's smaller than every other length scale of your theory. Okay, it is a dimensionless quantity. First of all, it has to be dimensionless. If something is not dimensionless, you cannot make it zero. Right? So it must be, first of all, I have to make a suitable dimensionless parameter, and then I should be able to treat it as small as I want. And then think of every expression as being corrected order by order in lambda. So as soon as I take lambda goes to zero, my interacting field theory must boil down to the free theory. Now this is not true always. You can have interactions which does not have this property. For example, QCD. QCD is not, I mean, it is only asymptotically. Okay? You cannot always take an interaction parameter. You cannot always treat an interaction perturbative. And if you cannot do that, then the solution that I have provided you does not. It is only valid if you can treat the interaction perturbative. Okay? Which is actually good enough for a huge bunch of theories and huge bunch of physics that we encounter. But not true for everything that we encounter. There are some interactions that cannot be treated perturbative. For example, black hole. In gravity, when all gravitons really couple with each other and form the black hole, that is not an interaction that you can take to going to zero limit. Only when it is very strongly interacting, then only black hole is formed. You cannot think of the whole process being weakly interacting. It's not weak. You cannot treat it perturbative. Okay, so there are some physical effects where this perturbation would not work. And if that perturbation does not work, then the entire process that I am giving you to compute the 2-point function and higher point functions in interacting theory will not be useful. But in many, many theories, for example, our good standard model, you can do this. Young-Mills theory, you can do this. Electromagnetism, you can do this. Okay? So wherever you can treat things perturbatively, you can always find this procedure useful, and you can compute any endpoint correlation function in the interacting theory via your knowledge of the corresponding free theory. Okay, clear? So this, all these subtleties actually comes out very cleanly if I would have done the if I would have given you all the algebras, but unfortunately that just requires a lot of time. Not just time, I also think that it is not useful to do it on an iPad. No, so huge an expression, and then in one page of iPad I can only give very little bit of it. So I will share my notes, or forget mine. My notes are not that great. You can just read Peskin. Peskin is very good, and that has all of it. All the derivations are there in this. So that's it, and we are good that at least for a huge class of theory, I can now compute a 2-point function. And of course, now like, see, if this is the expression of 2-point function, now let me give you the expression of any n-point function. You will agree with my whatever I'm going to write. Xn. By this also, I mean, I want to compute this omega, some time order product of phi x1 to some phi xn. Okay, omega. And this will now just simply become 0 time order product of all these guys, phi x1 to phi xn, then exponential of this operator minus I dt hit 0, and then in the denominator it is just this time ordered of exponential of minus. I'm not writing the limit, huh? I don't have space. Hit 0. Okay, so now you don't care. I mean, now we really don't care. Give me as many operators as anybody wants me to compute. I'll just insert it and evaluate this integral order by order in lambda. Okay, see, this is an exponential. No, the first term is always 1, and then the second term would be 1 hi. The third term would be 2 hi's, and so on. So that's all. That's what is this expression. Have you understood the expression? Little bit about this in the sense of perturbative QCD. I will do that. I will talk about the QCD towards the, I think in the last lecture. Okay. This expression is clear? Okay. Sorry, I have not derived it. I have given you the biggest if and but just as a statement, but I hope you understand that. If I do that, then I cannot draw anything. Now we will see, we will do something actually interesting, and you will not feel that bored even in an online class if I do that. Okay, let's now compute. बहुत हो गया, मतलब ज्ञान. Let's compute. I was only giving you gyan. I would have probably just started with this expression, but I find that very absurd. So let's compute G2 xy. Just 2-point function I'm going to compute and say we will do it up to lambda square order. Okay. So let just one more line I want to write it. Let me write it as n by d. By n I mean the numerator, by d I mean the denominator. Both the sides I have to compute, and then eventually I have to take this division to find the result. So this I want to compute. Okay. So basically what am I trying to compute? I am trying to compute this quantity omega, this pi x, pi y, omega, omega, omega. Okay. Now I'll first compute it to the order lambda to the 0. Lambda to the 0 matlab hi is simply 0, right? Because you remember, right? Hi, I hope you all remember. Okay, if you're not, let me. Lambda by factorial 4 integral d4x pi I to the power 4x. Okay, so if I take lambda to the 0, then there is no hi. Then what would be my n to the 0? N to the 0 is limit e going to infinity. Okay, I'll take the limit absolutely at the end. Then n to the 0 is nothing but 0 time ordered product of phi ix, phi iy, 0. What is the result? जल्दी से बता दो रिजल्ट क्या है? बताओ. Isn't this is this? This is just free theory of operators. Phi ix is nothing but my free operators. Yes, only h. Yeah, phi if is just free, exactly. I only have hf. So phi ix's are just simply the operators of my free theory. And this 2-point function is what we have called our Feynman propagator. Right, so the first term in G2 to the order lambda to the power 0 is nothing but our good old Feynman propagator. If I have to draw the diagram, then that's it. Okay, ये तो obvious है because I have not taken any interaction. Now comes the fun. Lambda to the 1 order. Okay, so now my HIT is not 0. Okay, so now what is my numerator? N, first order N, is minus I lambda by factorial 4, 0 time ordered product of phi I x, phi I y, integral sum z d4z, phi I to the power of 4z, 0. Okay, so I have three operators now. I mean, more than three operators, but operators at 3 point. One operator at point x, another operator at point y, and another operator at a point z where z is integrated over entire space. Okay, good. Now, what is this? Let us think about it. So I have three operators at three position. One is external ones are x and y. I'm just going to use two different colors so that you can understand. And internal one, I call this internal because this is integrated over. Huh? So Z, I'm going to use green color just to keep in your mind that whatever is integrated over is different from whatever is not integrated over. After, when you evaluate this result, your final result will not depend on Z because Z is integrated. So it will only depend on x and y. Now what do I have? At x I have one field, at y I have one field, but at z I have four fields. Okay. Now what kind of, I have told you the Wick's theorem. We know Wick's theorem. So we know that this entire expression, this is a time ordered expression, right? I can write this time ordered expression in terms of normal order and then all possible contraction. And only that term will survive where all the legs are contracted. Otherwise, the normal ordering will always kill that final expression. So now let's think what kind of contractions I can do. I can just contract these and I can contract this and this. This is one possibility. Right? Agreed? This is one possibility. But is that all? Well, no, that's not all. I have more. This, x, y, z. From z, I have 4 lines. From x and y, I always have one line. No, this is a possibility. Here also all the lines are contracted. Okay, so I will have both of these diagrams. Correct? And what is D0? What is D1? What is D1? D1 is nothing but just I don't have these external points, right? That's what is the definition of D. It's just omega, omega. Let me go back. You see there is no external point in D. So D naught is simply going to be just the vertex. I only have the vertex in D. And if I only have the vertex, then the only possible diagram is this. That's all. That's what is D1. So I know N1, I know D1. I can just find their ratio and that's the result. So I am not in these lectures, I'm not really ever going to tell you that what do I really mean by finding the ratio. But I hope you know that although I have written it as a diagram, but they all have integral representations, right? This line means something. So actually, if I really ask you, can you tell me what is the final contribution from this guys? The contribution is 1 delta f x minus y and 2 more delta f but at 0, right? Because they are at the same point, z minus z. So 0, 1, 2. Whereas this guy has 1 delta f x minus z, another delta f, y minus z, and another delta f at 0. These are the results. And you know the integral representation of all of them. So this guy is also delta f square 0. And then I can evaluate the integral and then take the ratio. But am I done? Have I given you everything in whatever I have written? What do you think? Is there anything that I have not been careful about? See, maybe many of you know QFT, okay? But I really want you to come out of your known thing and just look at the diagram, look at the expression and tell me that have I missed something?
The time ordering, I mean, we have not.
I have time ordered. These things only is meaningful when they are time ordered, right? So the expression that I have given is already time ordered, and only when you are taking time ordered operator, you can replace it by delta function. I mean, by that I mean Feynman delta f
So,
operator.
so we must have explicitly known that which of the point are earlier in time, x, y, or z, and
Exactly. So that is what this operator will do. You are right. That is what this operator will do. It will time order it and then evaluate it.
okay. So if z is occurring before y in time, then can we write z in between this loops? I mean, when we will assign
No, no,
arrow.
no. No, no, no. That I mean, so okay. So in this expression, I'm always going to take that x0 is greater than y0 in and is that is greater than anything that is integer. I mean, my referral point is. That's okay. See, your final result will not depend on z. You have to integrate over z. So no matter where you put it. So if your doubt is then, ma'am, how am I contracting x with z? It will only be contracted for that part when the time ordering is maintained. If it is not maintained, then the other part of the, you remember, na, expression of Feynman propagator, it has contribution from both time ordering. If x naught is greater than y naught, it picks up a piece. If y naught is greater than x naught, it picks up another piece. So here also, in both the cases, it will pick up the, for respecting delta x, it will pick up the respective contributions.
Okay, so only one of them will be true accordingly when we assigned it, which is earlier or which is later.
Yes, exactly. But exactly, but if that is not true, another way for z, since z is integrated over, no, so z will run over all possible values. So
Okay.
for some values of z, it would be less than x naught. For some values of z, it would be greater than x naught. Say similarly y, and then either part of the Feynman propagator will contribute.
Okay, so the
Okay,
physically the propagator will follow either of the path, however, since they are contributing, mathematically they will be here.
they will be contributing because that's exactly what Feynman propagator does. It takes contributions from both the ordering, right?
Okay.
But if other than that, I have missed something else. Can any of you see? See, please understand that this z is very special. I am integrating over z, and from z, there are 4 lines coming out. These 4 lines have absolutely same status, right? Because I'm integrating them over. There is no reason to, all I'm trying to say is there are 4 lines, right? 1, 2, 3, 4, right? 4 lines are coming because you are doing 5-4 theory. If you will do a 5 cube theory, then 3 lines will come out. If you will do a 5 to the 5 theory, then 5 lines will come out. But how many lines are coming out from this vertex? This is called vertex. Vertex means which is going into the interacting part of the Hamiltonian. So the interaction in the interaction vertex, all the lines are of equal status. So who told me that I only have to contract 1 with 2? I could have contracted 1 with 3, or I could have contracted 1 with 4. Isn't it? So this is a possibility where I have contracted 1 with 2 and 3 with 4. But I could have done this. I could have as well done this. Or I could have as well, now I don't know how to draw, but done this. And all of them would have given me delta f square 0. Right? So I would not know if I'm just looking at the expression, all of them will give me same expression, and that is delta f square 0, which simply says that the result that I wrote is not really correct. It is correct up to a factor of 3, because there is 3 ways of getting the same diagram. So far the diagram and hence the integrals are considered, you don't see any difference if I would have contracted it in any of the other 2 ways. So the result must be multiplied by a factor of 3. Okay? This is called combinatorial factors, and that you have to take care of when you are doing QFT. combinatorial factor. Similarly, let's look at the next one. So this vertex has 4 lines. See, so please understand that in any endpoint function, what is special are the n external points. These x and y are very special. That is a given data, given x and given y. But the vertex is like all its legs are equal. So see, this x could have gone to any of the 4 legs of y. The result would be same. Once that is done, only 3 legs are left. Then y can join to any of the 3 legs. And once that is done, you have nothing else to do. Only 2 legs are remaining and that just have to join. So this is the combinatorial factor for the second diagram. This one is definitely again 3. Okay, that's the result. So the result is not just drawing the Feynman diagram and writing the corresponding expression, but also understanding what would be the combinatorial factor and then take that into account. Okay, so now you have computed the 2-point function in 5-4 theory up to lambda order. And you see already your result is different from just Feynman propagator. To leading order, the result was Feynman propagator. But now you also have that plus minus I lambda by factorial 4 times this whole quantity. 3 into delta f x minus y times delta f square 0 plus 12 into delta f x minus z delta f y minus z and delta f of 0. This is just in the numerator, similarly in the denominator. Okay, good. So is it okay, guys? Have you understood? I know, yeah. Maybe when I was like a graduate student like you, it took a lot of time to get the combinatorial factors right. So I am not asking you to get the factor right. I am asking you to understand that there would be these factors. Okay, first you should understand that. If you understand that aspect in these lectures, you can find the right combinatorial factors in a month or 2 months or maybe like 6 months. It's not that big deal. But what is important to understand that external points are always special, so I cannot play with them. But internal points are vague points. I mean, all of them are of same weightage. So I can choose any one of them and the result is not going to be different. This brings in an ambiguity and we have to take care of this ambiguity. Okay, good. So now we are bold. Let's do more. Let's go to lambda square order. Okay. N2 is now minus I lambda by factorial 4 whole square. Remember, recall it was coming from an exponential. So second term is 1 over factorial 2. Then 0 t phi y phi I x phi phi I y. Now two such h's, right? So one d4 z phi I to the power z, another d4 w phi I to the power 4w, time ordering closed 0. So this is what I have to find. ठीक है. What does that mean? That means now 2 external point and 2 vertices. Okay, x, y, z, w. And all possible contractions that you can find from here. So job is all possible contractions, all mean all, and combinatorial numbers. Once you have it, you have the result. Okay, let us just try to find, there are 7 different kind of diagrams actually. Let us draw. One is this, one is easy. So let me draw that first. This. Actually, I probably should use 2 different colors for 2 different buttons. Yeah. This color. Okay. So this is one diagram. I'm not going to give you combinatorics, you can find it. By the way, what would be the combinatorics for this diagram? Quickly. This is simple. Quickly. 9, 9. 3 for one and 3 for other. Simply 9. Yeah, please don't pressure yourself. It's okay. I mean, it's easy for me. I'm teaching you, no? I have like little longer experience than you guys. So what I say is very easy, need not be easy at all. Can be difficult also for people. So it's okay. With time it comes, don't worry. Let's just understand the diagrams. That's more interesting. So this is one diagram. Then another diagram is this. Here, I'm going to mix them. Okay. Yeah, I could have used like red color also to do this, but let me just do whatever I have done. So here the two vertices is completely connected among it, and the external points are connected among itself. This is one kind of diagram. The third kind of diagrams that you can draw is following. This is one, and then this, and then this, and this. This is another diagram. Your first goal is to make sure that all lines are contracted. If there is a line that you cannot contract, that particular term is going to give you 0 result. Okay? Simply because of Wick's theorem. Fourth diagram. So that's all that you can do without disturbing your external points. Now my external points are going to be connected. Okay, so and that's very interesting. What I'm going to do here, the combinatorics becomes very interesting. And this is why I probably should have not drawn with two different colors. Because you must understand that there is nothing special about Z and W. Both are integrated over. Right? So which one I'm calling Z and which one I'm calling W, although I have given here a different eigenvalue kind of colors to them, but they actually do not have any different color. They're absolutely same. So that you must understand. That will play a role in finding the combinatorics. Fifth one is this. So the way I am drawing, as if I am always giving a preference to the green one, but it's not like that. Yes. This is another possible diagram. Then sixth one is this is another diagram. And then the last one. These are all. Okay. You see, there is no legs that are left. Okay. So your homework is convince yourself that that's all. Second, find combinatorics. Okay. And as I said, it is absolutely fine if you cannot find the combinatorics. Don't worry. Just make sure that you understand that there is no other diagram that is possible. These are all possible diagrams. Even if you can understand that much now, excellent, good enough. Okay, so similarly, you also have to find D0, D2, sorry. And just keep in mind that D2 would be all diagrams without external leg. Right? Because denominator does not have external points. So basically just these three will contribute. Sorry, just this guy will be there, this guy will be there, and this guy will be there. Because for every other diagram, the vertex have connections with the external points. And in denominator, you don't have external. So this is the result. Okay. Now, although I don't have time, but I want to tell you something. Just notice, just can I compute? Let us just compute what would be the contribution of this, right? This is nothing but delta f square 0. Both are at same point. And then I am also integrating it over d4z. What does that mean? Recall the integrations. Integrations were from minus t, 1 minus I epsilon. This is only the time. T into 1 minus I epsilon. And then you were supposed to take limit t goes to infinity. And also there would be, so this is just dz0. But also there would be d cube z. Right? So the result, and this guy is z independent. So the result is going to be simply this number times 2t times the volume of space, 3 space. And then you are supposed to take limit t goes to infinity. Right? What would be the result? Result would simply be divergent. It would be infinity. No way I can come out of it. So all the diagrams actually, all the diagrams where the vertex is not connected to external leg, this one, this one, this one, in fact, this one, in fact, this one also, where there is one vertex which is not connected to external legs. As soon as you have that, these diagrams will give you divergent results. Then you might ask me that, then what are you doing? Are you telling us after these 4 lectures that you have given us a prescription where the result is infinity? Well, of course not. That's not what it is. It is very nice. It is really, really nice. You must have noticed at least one thing by now, right? That the numerator, just look at this expression. Numerator contains a divergent piece. The denominator also contains a divergent piece. That you have seen. Here also, the numerator contains 1, 2, 3, 4 divergent piece. The denominator will not have 4, but at least would have 1, 2, 3. Right? These pieces will be there in the denominator also. And now you can also understand that this 4th one that you have here will actually, you can also think of getting it from a higher dimensional one. How? How? Go back. This guy, this sort of a guy and the product of this sort of a guy will give you, right? This term and the 2 dots that I have given, this term and this term. These sort of things will reproduce this one, isn't it? Yeah, I'm doing very roughly, and one can definitely do it much more concretely. I must tell you that physicists, quantum field theorists, they are basically mathematicians. Although I might state you results like through diagrams, but all these statements are very rigorously mathematically proved. Okay? So the result is following that this n, you can always write it as all connected diagrams. I will define for you in a minute, times exponential of all connected bubble diagrams. Just let me write. And denominator is always, the result is exponential of all connected bubble diagrams. Okay. So what is a connected diagram? Connected diagram means diagrams where vertex is connected to external legs, external points, or external legs, we also call it external legs. And bubble is not connected to external leg. And connected bubble is, the nomenclature is bad, all vertices are connected among themselves. And if you have noticed, then divergence really comes from these guys. This leads to divergence. I mean, I have only shown you an example, okay, and you have already understood that these sort of diagrams will always give me a Feynman propagator, which is a constant because it is evaluated at 0, and then the space integral will left because every vertex comes with integral, right? So those integrations will be left. In this term, there will be 2 integrations left. So they will give me divergence. In this term, there will be 2 integration left. And there will be 2 integrations, 2 such expressions, but these guys are good because these guys is going to x to z. So they are not 0. So I would still be able to perform some integrals, but then some integrals will be remaining. Okay. So problematic things are those where the vertices are connected among themselves. Those are connected bubble diagrams and they will lead to divergences. One kind of or other kind of divergences. And what happens is when we compute this n by d, the numerator and the denominator, these divergences just cancels. So any endpoint function, particularly any 2-point function, is just the connected diagrams. Only connected diagrams is what will going to survive after the division, after taking the ratio of numerator and denominator, and that's your result. Similarly, any endpoint function is also only the connected diagrams. Okay? Only connected. So if anybody asks you to find the diagrams of a 2-point function, a 3-point function, or a 4-point function, you should never draw the bubbles because they will be cancelled eventually. Okay, to any order, to every order, your result. So, for example, if I would have asked you to find this 2-point function, say this G2 up to just order lambda, then you should not have given me, this term should not be considered. It's just this term which will contribute because this is not a bubble. Okay, this term should not contribute. Ultimately in G2, this term will not contribute. This term will cancel with the denominator. Okay, that's what the idea is. Similarly, if I would have asked you to compute it to the next order, you should remove all the bubbles and just give me the contributions from the connector. You can do this calculation. You can really find all the terms and then take ratio and then check that all these diverging terms are cancelling between the numerator and denominator. At least for this theory with all combinatorics numbers, you can do it up to lambda square order. Okay? After doing it up to lambda to the power 4 would be very dirty, but at least up to lambda square order or even doing it till lambda cube would be dirty. But till lambda square order, you can definitely do it by hand. Or just agree with me, whatever I have said. Okay, both are okay. So that's your result. Okay, this is what it is. So in any interacting field theory, eventually all you have to find is just the vertex, the free propagator, and then draw all the connected diagrams and find the combinatorial factors of those diagrams. Add them up, that's your result. And that's all for interacting. We are done. Okay. So I am done. If you have questions, you can ask me, or let me just. So the points are find vertex. Second, draw all connected diagrams. Is find combinatorial factors. Add all, finally add all. That's it. If you do this, you will have any endpoint function in any interacting. Okay, so that's all. Tomorrow I'll give you, I'll think about it tonight. Either tomorrow I'll start electromagnetic theory and then I'll talk about scattering, or tomorrow I'll talk about scattering and then talk about electromagnet. I'll think about it today and then we'll do it accordingly. In today's tutorial, they will probably do a little bit more of diagrams, maybe some different theory, maybe lambda cube, 5 cube theory or 5 to the 6th theory. Okay, and of course, if you have more doubts, you can ask Orgho and Orindam. They are excellent. They are very good. So, do you have any other questions? Else I can discuss. I have already taken up 10 minutes of yours. Sorry. Yeah.
So,
Okay
Navamita,
then.
there are two questions in the chat box. Would you like to take it now or later?
Oh, I think I have. So
Oh,
only one question is, I have taken it during the lectures.
oh,
So
I
only
see, I
one
see.
question, yeah, only one question is remains, which is related to perturbative QCD. I talk about it once I talk about electromagnet.
Okay, okay, okay.
Ma'am, I actually have one doubt. Like a few pages back, where the omega state was defined, like when we were
Let me go.
computing the Z2. It went
Yes.
next page.
Hmm.
Yeah. So in this step, we have in the denominator omegas, like the inner product omega zero, like that.
Hmm. 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 Hmm.
So,
Hmm.
like if omega is like if both are not
Hmm.
the same, then the denominator will blow up. So just this and the what the thing that we were doing now, the
Yeah. So you are.
unit diagram.
So maybe, I mean, if I can understand, because the sound, the voice was being disturbed. But if I understand, then you are asking, probably you are asking that in the definition of omega, I already have omega, right?
Yes,
So
yes.
what is going on? Okay. So now
No, no,
let
no.
us.
No, no. I am asking like if omega and zero, we are taking the inner product of this. So the denominator will blow up, right? So does this somehow
Denominator
connect
will
to,
blow up. No, why should the denominator blow up?
oh, the contribution come from e to the power minus I, the exponential factor will,
So, this is the most dominant term, right? It will not
okay,
blow up. This is the,
okay.
because E naught is very small. In fact, in most of the cases, we are going to this E naught. I am going to set my scale such that E naught is 0.
Mm-hmm.
Right? So that is why this is the most dominant term that will survive. Every other term with respect to this term will be suppressed, and hence in the denominator that will create divergence. But they are not even there, right? In the earlier step itself, in this step itself, these other terms have been suppressed. And this piece is not, it is the most dominant term. And as soon as you change your scale and set E naught to 0, then this part is not a problem at all. Right?
Got it.
And yeah, and the factor that you are still left with this, you see, that is why in your 2-point function I have actually these guys and these guys, right? So this omega definition will bring in a factor of that this one will have a omega 0, this one will have a omega 0, this one will have a omega 0, and that one will also have a omega 0. So all this, whatever number it is, they will cancel from numerator and denominator,
Okay.
and eventually will not affect my result. Okay.
Got it. Thank you.
So what I will do today is just today I will share the class notes. Okay, the one that we are discussing here, that we have discussed here. But at the end of my lectures, I will share detailed notes of QFT. There, all these derivations are also there. Okay, that will probably help you guys because I could not do all the derivations in that. Yeah, okay. You can, yeah, others can leave. We might, yeah, you have a class in 2 minutes, no? So bye bye. See you tomorrow.
So science sir is here already. So can we start, say, after 3-4 minutes later? You can take, sir, probably 5 minutes from the lunch break.
Yeah, sure, sure.
Okay.
Developer, are you there?
Yes, we can start probably. No?
Yeah, Professor San, I think we can start.
Sure, sure. Okay. Okay. So let us start from where we stopped yesterday. So yesterday we kind of used the whole class to understand only one thing, apart from, of course, deriving this expression of the Riemann tensor. The important thing that we discussed yesterday is something which is known as the geodesic equation. And today also, at least half of the class, we will devote time in discussing the geodesic equation. So geodesic equation, as you might understand, as the name suggests, and as we stressed yesterday in many different contexts, that this is basically the tells you the motion of the particles and the path, the trajectory that the particle takes. And if you remember, yesterday we start our discussion with the special relativistic expression for this, and that we said is nothing but this equation. And we gave a very simple definition that if we take the tangent vector to a curve and ask how much does the tangent vector change along the direction in which it is moving along the curve, then the answer is 0. Because one of these, I mean, this is basically your tangent vector, and this is the change in the tangent vector as we go ahead along the curve. If I draw the plot or the word line of a particle, then at each and every point I can define a tangent vector, and then I ask how this tangent vector change as I move ahead. And not to our surprise, we find that the geodesic equation is basically, I mean, in the special relativistic case, is giving you 0, and that is expected because this is the simplest definition of a straight line. In the case of a straight line, if you try to draw the tangent to a straight line, that tangent does not change, it just move ahead. Okay, so in special relativity, therefore, we knew how a tangent vector changes along the curve to which it is tangent to. Therefore, we ask the question that, fine, this is the trajectory of a free particle in flat space-time, but does this actually go through if my space-time is curved? Or in other words, whether this equation remains covariant if I go to some curved space-time. So the question is, does this remain covariant under a general coordinate transformation? That is the question that we asked, and the answer definitely that no, it is not, because if I actually take this derivative part, this derivative del nu u mu, if I look at the changes, that means they are primes, then I knew that even though there will be one term which will always remain, give you the proper transformation property of a tensorial object. However, for such expression of derivative that we have written here, there will always be a second term, kind of an inhomogeneous term containing a second derivative that will break the tensorial property of this derivative term. So this is the problem that we had faced, and then we asked this question. So this actually creates all the problem, because then I cannot say that this object transform covariantly under a general coordinate transformation because of the presence of this term. So then we ask this question that what is the generalization of this equation that we have obtained in flat space-time? And we also, so we basically ask two questions. So what is the generalization of under general coordinate transformation? And the second question we asked is that why did we not get the equation in a covariant form in the first place? Of course, I mean, you can say that because of we already knew that the derivative of a 4-vector does not transform properly under a general coordinate transformation. That is why we did not. But in the first place, why did this come? This came because we started the whole discussion with an action which is not invariant, which is not generally covariant. So the action that we took from our special relativistic approach was this. But we knew that this is not going to work, and that is why we actually had to introduce the idea of a metric where this metric tensor G mu nu will depend on some x alpha, which is both space and time. So this is the correct thing to be incorporated in the action. So we need to replace this, and then we did a whole lot of variational calculus and figured out what will be the equation, and the equation that we have obtained by varying this action sitting there. So basically the action that we have looked for was this, and maybe we should write covariant. And this basically gave us the equation. If you may recollect your memory or look at my notes from yesterday's class, this is something which is known to you, and this is something which we had rewritten again, because this is the equation, and then we used some properties and we used some tricks to basically obtain the more well-known form for the geodesic equation, gamma nu say beta lambda u beta u lambda equal to 0. And we remember that the Christoffel symbols can actually be physically obtained in terms of the metric and its derivative from this exercise. These commas, because many of you might be encountering the notations for the first time, the commas represent partial derivatives with respect to x alpha for this term, with respect to x beta for this term, and with respect to x lambda for this term. And semicolons of always represents covariant derivative. There is another useful notation which many books actually use, which is this notation, which is nothing but the same object but without this term. Some books also use the expression that I am just writing here. So this is our well-known geodesic equation. Both of these are basically two different forms of the geodesic equation. So, I mean, this governs the motion of the material particle in a given gravitational field. And of course, this is same as, I mean, both of these are same because this is in terms of the for velocity. I can always write it in terms of the position by noting that, sorry, this first term is nothing but d2x nu d tau 2 plus gamma nu beta lambda dx beta d tau dx lambda d tau equal to 0. Sometimes we also write this as x dot beta, and this is written as x dot lambda, where a dot represents derivative with respect to the proper time tau. Okay. Now, oops, what happened? Okay. Somehow there is, this thing is not responding. Okay, it is allowing me to write, but not allowing me to, okay. Yeah, So, as we stressed quite frequently yesterday, that this geodesic equation, which we have written, du mu d tau plus gamma mu alpha beta u alpha u beta equal to 0, this geodesic equation does not necessarily always mean that my space-time is curved. Why am I saying that? Because suppose I give you a metric which is nothing but the metric of a two-sphere. This is the metric that I have written in the polar coordinate, but this still represents flat space time because the time part I have not taken care of here. So there is no way you can say that this is representing curved space time. It's just that the metric of a two sphere. Now, if you calculate the Christoffel symbols for this metric, you will find that the Christoffel symbols are non-zero. And these Christoffel symbols being non-zero, therefore, does not necessarily mean that you are in a flat space-time. So, gamma mu alpha beta non-zero does not mean that my space-time is effectively curved. It does not mean that. It does not mean that. You may get non-zero gamma mu alpha beta even for a straight line if you write the equation of the straight line in polar coordinate, which is what I have shown yesterday. So just to remember, just to recollect that the equation of a straight line, you can always write in a parametric form, and you can write your equation by choosing an appropriate parameter which may be thought of as an arc length, and you can write x and y coordinates as x equal to s and y equal to alpha s plus beta, and accordingly you will immediately find that your equation for x and y in terms of the parameter s will give you this set of equations as the equation of your straight line. And if you calculate the Christoffel symbols from here, you will clearly see, or you will clearly find that this gamma mu alpha beta equal to 0. However, you try to write down the equation of the straight line not in a flat space-time or not in a apparently linear parameter, using the linear parametrization or in Cartesian system. You use the polar system, polar coordinates, and immediately you can, yesterday I explained why this is the equation. This equation represents the equation of a straight line, and immediately you will arrive at the equation d2r ds2, which is something which is not 0, rather it is some non-zero number, some number or some expression, and this something is nothing but your gamma mu alpha beta. So even for a straight line you can get non-zero Christoffel symbols. That is the first lesson that we obtained from this discussion. Second important point about the geodesic equation, which we did not discuss in yesterday's class, is that this equation that I have written, du mu d tau plus gamma mu alpha beta u alpha u beta equal to 0, this equation of course is always generally covariant. There is no doubt about that. But if you look at the terms individually, the first term being a partial derivative or being a derivative, and the second term be containing the Christoffel symbols, none of these individually are generally covariant tensors. None of the first term, neither the first term nor the second term individually is a generally covariant tensor. And therefore, even though the whole equation as a whole generally remains covariant or is written in a covariant format, its covariant nature is not explicit if I write the equation in this format. Therefore, we write the full equation in a generally covariant form in the following way. So I will take this equation and I will write it as del u mu del x rho, and then dx rho, I'll just use the chain rule, plus gamma mu alpha beta u beta equal to 0. So the same equation I have written from this line, I have gone to this line. And this I can write because del x dx rho d tau is nothing but the 4 velocity. So I will write it as u rho, and this term which is in this circle here, this I will write as del rho. Del rho is nothing but del x rho u mu plus gamma mu, and in this expression I note that I have beta and alpha both are repeated indices, therefore they are dummy. So I will exchange one of these indices, say beta, with rho. Okay. I have not done anything which is not allowed by the rules. I have just changed this beta index because it is repeated, and that means it is summed over, and that implies that it is a dummy index. I can replace beta by any other alphabet there in this Greek vocabulary, and I happen to choose this as rho simply because then I can take this u rho common from both these terms. And if I take u rho common, then this becomes del rho u mu plus gamma mu alpha rho u alpha, and this taking this u rho common, which is what I was telling. But I am sure that by now all of you have identified this object. What is this object? Any of you want to respond? This object that I have put inside a square or rectangular area. Anyone willing to comment? This is nothing but the expression of the covariant derivative of the vector 4 vector field u mu, right? So this is what is exactly the covariant derivative with respect to rho and u mu, because this object is del rho u mu, or in our old notation, this is u mu semicolon rho. Both these notations I am using kind of in an alternate way, but this, why am I writing this in this format? Because this actually gives us this is the same geodesic equation. So we now have 3 different forms of the geodesic equation, but this form is more useful visually because it contains the covariant derivative, and with covariant derivative we are happy because then we know this expression contains 4 velocity, this expression contains a covariant derivative, and therefore the geodesic equation written in this compact form definitely should be a generally covariant format, and it is a proper tensor equation. Now, let me go to a very crucial part of the discussion, and you may have heard the name. Uh, the discussion is about what is known as affine parameters. And at the end, we will also discuss something which are known as null geodesics. And we will see how null geodesics differ from our like standard material particle with mass time-like geodesics, and how to parameterize them. We will talk a little bit about that also. Now, when the geodesic corresponds to the path taken by a material particle, we know that it is very natural to for us to use the proper time as a parameter for the curve, because I I hope that all of you remember the definition of proper time. It is nothing but the time that the moving observer is seeing in his or her clock. And therefore, if I am moving in space time and if I am carrying a clock, then at each and every point on my trajectory, I can actually assign the coordinates with the help of my clock. So now it is 11 minutes past 12. So at this point, if I am moving with say some velocity or acceleration, I can assign that at exactly this point I am in this location. So one event is there. Then the next moment I assign a different coordinate according to my clock. So this is the way a material particle which is having some mass can assign to each and every point of his or her trajectory. So assigning coordinates is easy, and it is natural to use the proper time as a parameter for the curve and to write down the geodesic equation as d2x mu d tau 2 plus gamma mu alpha beta x dot alpha x dot beta equal to 0. But a geodesic in space-time, like any other curve, is just another curve. Of course, it is a geometrical entity, and therefore, since it is just another curve, it should not only be parameterized by the proper time tau. There should be another way to parameterize the curve. There should be an infinite number of different ways to geometrize or to parameterize this curve, and therefore this curve, which I am calling a geodesic, should be treated as a geometrical entity that is independent of the parameter. So this is a crucial point, that geodesics, after all, geodesics are just curves in space-time. And therefore, this implies they should be independent of parameters. I can choose parameters on my own, just like the example of the straight line. I can choose Cartesian system, I can choose polar system. It does not matter. So if you may recall that I had my action, which we started with as minus m d tau, and this was written as root minus g mu nu dx mu dx nu. And in the next step, we wrote, because we needed to parameterize it, as minus g mu nu dx mu d tau dx nu d tau, and d tau comes outside the square root. So this is parameterized. So this is what is called parameterizing with respect to proper time. And this actually led us to the geodesic equation. by variation of this action, and then at the last point, at the end stage, claiming that the variation at the endpoints vanishes, gave us the equation of motion, and that equation of motion turned out to be nothing but the geodesic equation. And the geodesic equation, this term tells us that essentially, so this is what? This is nothing but the acceleration. So this tells us about the force. So I will come to that at a later stage. So now I am claiming that why only tau? I can parameterize my curve by any parameter. So we write, or we claim that let us not be bogged down with parameterizing my geodesic by tau, the proper time. Rather, I claim that it can be any function of lambda, and lambda is some other parameter. I do not know what it is, but it can be anything. And then I immediately can write this dd tau, because the expression of the geodesic contains dd tau and d2 d tau 2. So this is d lambda d tau dd lambda, and I will write it as 1 by d tau d lambda dd lambda, and this implies that d tau d lambda is nothing but f prime lambda, okay, where prime is derivative with respect to lambda. So this is, I will write it as 1 by f prime dd lambda, right? I hope everything is clear so far. Now I will write d2 d tau 2, which is dd tau of 1 by f prime dd lambda. And if you do the algebra, it will turn out to be, first this dd tau will operate on 1 by f prime, and it will give me sorry, let us first assume that okay, let me write another step. So this dd tau, I will write it as 1 by f prime dd lambda and 1 by f prime dd lambda, and this is going to give me 1 by f prime square d2 d lambda 2, when this dd lambda operates on dd lambda. This is the first term, and then I will have 1 by f prime f double prime by f prime squared dd lambda. So d2, the geodesic equation in terms of the proper time as the parameter was this. But now, since I have changed my tau to some function of lambda, I will use this expression for d2 dt2 in here, such that I get 1 by f prime d2 x mu d tau 2 plus minus 1 by, or let me write directly, f double prime by f prime squared dx mu d lambda plus gamma mu alpha beta 1 by f prime dx alpha d lambda dx beta d lambda equal to 0. So final result that will come out of this exercise is something like this. If I multiply by f prime, this is plus gamma mu alpha beta dx alpha d lambda dx beta d lambda equal to, I take this on the other side, f double prime by f prime dx mu d lambda. So this I have already seen just now, that can be written as u rho del rho u mu is equal to f double prime by f prime u mu. But remember, this u mu is del x mu del lambda is not the 4 velocity. Okay, it may be some velocity, but it's definitely not the 4 velocity, because 4 velocity is defined with respect to proper time. Okay, so this equation that I have written is a slightly general form of the geodesic equation, and this also tells us that it actually does not restrict the parameter that is used to describe the geodesic. The parameter here to describe the geodesic is completely arbitrary, but you note very important things here. Firstly, if tau is a linear function of lambda, this is very crucial. If tau is a linear function of lambda, what happens? You look at the right hand side. If say tau is a linear function of lambda, that means lambda I defined as tau I think I defined as f lambda. Where is it? Tau I defined as f lambda. Tau is f lambda, and I am claiming that tau is a linear function of lambda. That means maybe it is a lambda plus b. Suppose it is linear in lambda, and therefore if I take the functional form f lambda is a lambda plus b. Therefore f double prime will become 0 if I take double derivative of f with respect to lambda. So therefore, if tau is a linear function of lambda, the right hand side of equation, let me number these equations now. Suppose this I number as equation 1, this I number as equation 2, and then this is equation 3. So the RHS of equation 3, it should be 0 if tau is a linear function of lambda. And we get back the old geodesic equation, which we wrote down in equation 2, and therefore it is basically same as tau. It says that if lambda comes as a linear function, I mean if tau is a linear function of lambda, then it is same, it is giving you the same geodesic equation with the right hand side being 0. This goes to 0. So, so this implies that there may be a class, a set of parameters or class of parameters related to each other by linear transformations which preserves the form of the geodesic equation. And these are known as affine parameters. That means they are related to each other by linear relations, and all these parameters will give you the same right hand side of the equation. That means zero. Geodesic equation, that means zero. Now let me state one thing quickly, and then I will go to the discussion of the null geodesics. The other important property here is that it is also possible to provide several other variational principles from which the geodesic equation with an affine parametrization can be obtained. For example, let us start with another type of action. Instead of starting with the tau, let us start with lambda, and let us write it in this manner. Note that there is no to the power half or square root of this thing. This is what we have defined. So this is essentially nothing but classical mechanics problem, where lambda is playing the role of time, kind of, and x mu is playing the role of generalized coordinates, so that you can write your action as L dt. So variation of this action, this particular action, keeping x mu fixed at endpoints, will lead you to the well-known Euler-Lagrange equation, which is del L del x alpha equal to dd lambda del L del x dot alpha. So this is the Euler-Lagrange equation. Now, if you actually look at what is del L del x alpha, what is del L del x alpha, you will immediately find that this is nothing but, because your L is this object, so you will find that it is nothing but del G mu nu x del x alpha dx mu d lambda dx nu d lambda. And the second, the right hand side, which is dd lambda of del L del x dot alpha, this will give you twice dd lambda of g alpha mu u mu. Okay, so this is something which is clearly obtainable from this Lagrangian. Okay, this two term comes because there are these two derivative terms. So now you immediately equate this with this, and this will give you therefore half g mu nu comma alpha u mu u nu, which is equal to dd lambda of g alpha mu u mu. Or we may also write du alpha d lambda equal to half del alpha g mu nu u nu, but isn't it the same equation as equation 1? Same as equation 1. Only thing is that the parameter has been changed and the form of the Lagrangian also has been changed. There is no square root sitting here. Okay, so earlier our action, if you look at, our action was square root this thing. But what it says is that if you choose a different form for the action, you get the same geodesic equation with which you have started with. Okay, so this, of course, there is an of course here, provided, provided lambda is an affine parameter, then only this is going to happen. So now it says that variational principle based on the action A1. Note that this is not the action A with which we derived everything so far, leads to the same equation of motion. Okay, so variation of A1 with respect to okay, so variation of A1 leads to the same equation of motion as in 1. Only thing is that the parameter has been changed from tau to lambda. And therefore, another important observation in this context is that if I define the object Q as g mu nu x dot mu x dot nu to the power half, where the dot denotes the derivative with respect to the affine parameter lambda, then our original choice in this action, A, action A was L equal to Q. Okay, so then both these Lagrangians would be the same. And the choice for A1 with which we started was L equal to Q squared, but both gave same equation of motion. However, the action A was reparametrization invariant. This is very crucial because I said that the one that we are using here with respect to tau, there is a term, there is a terminology rather, that is known as the action being reparametrization invariant. And this reparametrization invariant is a very, very crucial property of this type of actions that we are considering here. On the other hand, it is not necessary to choose an affine parameter with this action, but more general action like the one that I have written in A1 will lead to the correct equation of motion only when an affine parameter is chosen as the parameter. So for this, affine parameter is the choice. Okay. Now let me come to the final part of the discussion on geodesics. We have discussed very important properties of geodesics so far. And now we are going to discuss the last topic, which is what is known as different types of space-like, time-like, and null. So if we are given a geodesic, then we can think of a tangent vector to it. And this u mu is kind of represents the velocity. In our convention, Remember what was our convention? Eta mu nu was -1 plus 1 plus 1 plus 1. So in our convention, any vector which is negative, whose norm is negative, is known as the time-like geodesic. Anyone space-like but there is also another class where u mu equal to 0, and they are known as null geodesics. Now I am going to prove another theorem which is very useful, and the statement of the theorem is as follows. If a geodesic is either time-like or space-like, null at a given event, then it will continue to remain so. So that means if by some means I have identified that it is the vector which is time-like, then as you move ahead on the geodesic, the vector will always remain time-like, it will not change. So to do so, we are going to first show a little bit different expression, or we will first prove that. We first show dd lambda u upper mu u lower mu equal to u rho del rho u mu u mu. So I will start with, to show this, I will start with the right hand side of the equation, u rho del rho u mu, and I will write this as dx rho d lambda, u rho as dx rho d lambda, del rho u mu, sorry, no, that's fine, u mu. So this, sorry. So then I will use the chain rule here. U mu. And this I know I can write dd lambda u mu. Since u mu is a scalar, because u mu is a scalar, that we all know, this implies that del rho is same as the partial derivative is same as the covariant derivative. So u rho del rho, let us start with this expression now, u mu. This is, I will write as u rho del rho u mu u lower mu plus u mu del rho u lower mu or covariant mu. This is something which is u rho del rho u mu u mu plus u rho u mu g mu nu del rho. I have just raised the lower index to up, and I have also used the metric compatibility criteria because del rho g mu nu is equal to 0. So I hope all these steps are clear to you. So this will therefore become, it will remain as it is, u rho del rho u mu, u rho del rho u mu plus this now will become g mu nu u mu will become u rho u nu del rho u upper nu. Please correct me if I am making any mistake somewhere. Twice. So these are two same terms if you look at it carefully. The only thing is that you can say that this nu is summed over. So instead of calling it nu, I will call it mu. Okay. So this will give me twice, sorry, u rho del rho u mu equal to 0. This is because u rho del rho u mu is our known geodesic equation. So therefore, this tells us that if I know the nature of the geodesic curve, whether it is time-like, space-like, or null, it does not change its nature as I move ahead on the geodesic. So u mu is a constant along the geodesic curve, and once it is time-like or space-like or null, it continues to remain so. Okay, so this is what I wanted to talk about, the affine parametrization and other things. There is another very important aspect that is related to null geodesics, because in general relativity we will often encounter the motion of light in curved space-time. So null geodesics are an integral part of our discussion. So I want to spend some time on null geodesics. So a null geodesic will be the path, as you all know, which is taken by a light ray in a curved background. And just as the time-like geodesic describes the path of a material particle with some mass. However, there is a problem for describing null geodesics, and the problem is that we cannot use proper time as the parameter. Why? Can anybody tell why we cannot use the proper time as the parameter? As the parameter to parameterize the curve. Anyone willing to answer? Oh, where is that link gone? Okay. Anyone willing to answer this question? Why we cannot use proper time as the parameter to parameterize the null geodesic? Well, I mean, you cannot use the proper time tau or arc length ds as a valid parameter for a null geodesic because they vanish along the path, because this is what null geodesics imply, that you are moving along the light cone geometry, the boundaries of the light cone. So ds square, which is same as d tau square, which is 0. So null geodesics are therefore, how do I actually parameterize them? Null geodesics are basically described using arbitrary parameters. They are defined as the integral curves. So the definition is that they are defined as integral curves of a vector field k mu x which satisfies k mu del mu k rho, which is equal to some fx k rho. So what is this object? As I said, we cannot use any parameter which is the proper time to describe a null geodesic. This one is the general geodesic equation. So f double prime by f prime that we have seen in our discussion today. So this is some function. And also null geodesic, since we are talking about null geodesics, this holds. Okay. But now you note, so together we need both these definitions. So together they define the null geodesic. But now you note one thing. If k mu or k rho, so the point is the following. If k rho is a null vector, then whether I multiply some function of x with k rho, it will also remain, it will be a null vector too, irrespective of what this arbitrary function mu x is. So therefore, this term, if I look at, if k rho is a null vector, fx k rho will also be a null vector. And therefore, we will have, so we can use this freedom, and make the right hand side of this equation equal to 0. So that means we will have null geodesics k mu del mu k rho equal to 0 with, of course, k mu equal to 0. So this is some kind of affine parametrization, and it is usual to choose the parametrization such that k mu is the momentum of the photon. That is how generally people work with null geodesics. Now the last thing, sorry, I said that this affine parametrization and the null geodesics will be the last thing, but the last thing really is something which all of you are familiar with, which are known as inertial forces. So the geodesic equation tells us that if space-time gives non-zero connection coefficients, then so that means if gamma mu alpha beta are non-zero, then there are two possibilities. One is, of course, because the space-time is curved, or the other one is the choice of coordinates, simply the choice of coordinates. It has nothing to do with the curvature of space-time. Rather, it is a choice of coordinates. So we observe an acceleration. So the equation, if you, again, let me remind you, d2x mu d tau square plus gamma mu alpha beta dx alpha d tau dx beta d tau equal to 0. This equation, basically, we observe an acceleration which is given by this, because this is nothing but your proper acceleration, even in the absence of an external force. Now, we are used to accelerations resulting from forces, right? All of you know that if there is a force, there will be an acceleration. And so we interpret the acceleration, which is x mu double dot, is the acceleration. So we interpret the acceleration that results from the connection coefficient results from gamma mu alpha beta as corresponding to an inertial force. Okay, so that means we know all of these things from our classical mechanics courses. F mu inertial should be nothing but we multiply it by the mass both sides minus m gamma mu alpha beta x dot alpha x dot beta. So the principle of equivalence tells us that the acceleration due to gravity for a single particle is indistinguishable from the acceleration due to a particular choice of coordinate. Now, since we know that the free particle follows a geodesic or free particles fall along the geodesics, the geodesic equation says that acceleration a mu, which is nothing but x mu double dot, is given by this expression gamma mu alpha beta x dot alpha x dot beta, which is to say that gravitation gives rise to an inertial force. Okay, so this you are familiar because Earth, if you are actually on the surface of Earth is an accelerating system because it is rotating. So now if you actually kind of put a fixed pole, and from that pole you put a pendulum and make that pendulum to round about or move in a circular path around the pole, then if you are actually sitting on the pendulum, you will feel a force which is radially outward, and that is something which is called the centrifugal force. Okay, so this is those kind of pseudo force or something which you actually see, and here also the similar kind of thing happens. Now I will end this topic now, and I will move on to the next topic, but in the tutorial I think Bhashwati will probably discuss the Christoffel symbols, the calculation of the Christoffel symbols from the geodesic equation. Why this is important? Because you see, if you give me a metric, then the methodology that I have described here, this methodology is going to give you the Lagrangian in terms of the ds square or in terms of this object. So you can actually write down the Christoffel symbols by studying the geodesic equations. What is the benefit for that? Because Christoffel symbols otherwise will be extremely large in number. There are three indices, mu, alpha, and beta, and not every index, I mean, not every combination of indices are going to give you a non-zero value. Most of the Christoffel symbols will come out to be zero. Now, if you follow this methodology that I have not described, Bhashwati will describe, that follows from this principle, that will give you or provide you with only the non-zero Christoffel symbols. Otherwise, if you start with the Christoffel symbols in terms of the derivative and derivative of the metric and product of the metric and multiplied by a metric, then that definition will lead you to evaluate each and every component of gamma, be it zero, be it non-zero. If you start from the first principle calculation, that means if you start from the definition of gamma mu alpha beta in terms of this metric mu rho times this, where these three derivatives terms of the metric were there. If you start to calculate gamma mu alpha beta from this definition, then the number of calculation, number of steps that you need to follow, the number of components of gamma you need to calculate is extremely large. So this will be discussed in the tutorial. Now I quickly go to the discussion on curvature, and we call this our discussion on some perspective on curvature, because we are always talking about curvature, but so far we did not discuss explicitly what it is. So the most important effect of curvature is that how it affects the relative separation between the nearby geodesics as the manifestation of real gravity. If you remember, at the very beginning, on the very first day, I gave you these two equivalent scenarios that we generally encounter, or that actually is given by the equivalence principle. One is that I am in a closed box very near the surface of the earth, and I am in a free fall. So the box is near, I'm not even near, free fall. This is just kept on near the Earth's surface, where there is some acceleration due to gravity, and the same box is taken into an interstellar space where there is no gravity, but the box is moving upwards with some acceleration which is same as the value of the acceleration due to gravity on the surface of the earth. The important thing is that mechanical experiments that you perform which involves gravity will yield identical result. That is the important part. Mechanical experiments involving gravity will yield identical results in both these scenarios. And this is what is your equivalence principle. But in order the equivalence principle should be valid, this is true as long as acceleration due to gravity of Earth remains uniform over the size of this box. So that means the scale over which the acceleration due to gravity is uniform, if that scale is denoted by capital L, and if the size of the box is small l, that means this is L, small l, then one needs to make sure that small l is very, very small compared to capital L. What was capital L? Capital L is the length scale over which the gravitational field changes, varies. So that means, as you know, if you are going above the surface of the earth with a certain height, the value of small g is going to change. But this, in order to change this value of g, you have to move a very larger height. And that height is capital L. And this small l, much less than capital L, makes sure that equivalence principle holds. That means equivalence principle holds. That means you cannot distinguish gravitational effects from real gravity from acceleration. That is what happens. The genuine gravitational effects cannot be revealed in a region of size L, small l. So this is so the ultimate conclusion of all this discussion is that any genuine gravitational effect cannot be revealed in a region of size small l, which is much less than capital L. So that is what is this, what this means. Now it can be shown, I will immediately show that the metric g mu nu can be thought of as gravitational potential. That means the gravitational potential and g mu nu are similar, and the Christoffel symbols will behave as gradient of phi. That is already known from our definition of Christoffel symbol, because gamma mu alpha beta contains derivative of the metric. Gamma mu alpha beta contains derivative of the metric. Therefore, if metric is equivalent to the gravitational potential, then gamma mu alpha beta is equivalent to gradient of phi, which is nothing but acceleration, which is clear from our geodesic equation, which is what we discussed so far. And therefore, any change in Christoffel symbols will lead to del of del phi. So this is the change in the gravitational potential in the second order scale is going to give you the curvature effect or the effect of real gravity, because gradient of phi is related to the acceleration due to gravity. And if acceleration due to gravity needs to vary, that means this term needs to vary, and therefore we need to look at the second derivative term, which is del of del phi or del square phi, which can come only from the derivative of the Christoffel symbols. Okay, so let me do a small digression and let me tell you why this phi should be related to the metric. It is true in the non-relativistic limit. So in the Newtonian case, I will discuss something. So recall that in special relativity, we wrote down the action as minus m square root minus eta mu nu dx mu dx nu in special relativity, and this was nothing but minus ds squared square root. And this we said to be the Lagrangian, and the Lagrangian was identified as, just go back to our discussion on the very first or second class, I don't remember, I think the second class or the first class, where we have expanded this. This is for free non-relativistic particle. But now if you ask, we need to insert some interaction, and I want to insert a potential. Suppose I want to insert the gravitational potential, a particle in a gravitational field is there, so I need to insert the potential in this Lagrangian. So this will modify the Lagrangian. I know it is nothing but the addition of term like minus m phi. Okay, so this is how the Lagrangian will be modified, and that immediately implies root over minus dA squared, which was there in the action. It will be written as 1 minus half v square plus phi dt. Why it is like that? Because it is clear that action is, so the action I think we wrote as A. Action is written as L dt, and L in our case we have written as minus m square root minus ds squared, and from this all of this will follow. Now you can use your v square as dx dt whole square plus dy dt whole square plus dz dt whole square. And if we incorporate these things into this, we will get my ds square as minus 1 plus twice phi dt squared plus dx square plus dy square plus dz square. So this immediately tells, this equation immediately tells us two things. One is that gravitational potential can affect or can change the metric, and this also tells us that we can always think of phi being affecting the metric, or phi being the gravitational potential being equivalent to the metric. Of course, this is not the full picture. There will be changes here also, but that discussion I am not doing right now. But what is more important is that non-zero gamma, which I can get in many scenarios, does not necessarily mean space-time curvature, and it will not provide any curvature effect alone. Non-zero gamma is not a proper way to check the curvature of space-time. What is the remedy then? The remedy is to probe the gravitational field, and we need to proceed to the next order. So that means we think of an experiment, we make our lift a huge one, a very, very big lift, and the lift is such that there is a change of gravitational field within itself. And if I have three different balls which are actually falling, so this, suppose the length of the lift is extremely large, it is much greater than capital L, over which gravitational field can change. So if I am in such a lift and if I start to drop the balls, everything is going to be attracted towards the center of the earth. So the trajectory of all these balls will be coming closer to each other. All these balls will be coming closer to each other, and as they are released from the height within the lift and as they are falling towards the floor of the lift, they will be moving towards each other. I mean, these two trajectories will be going closer and closer because everything is being attracted towards the center of the earth. And this effect, I am claiming that this effect only comes because of terms like del nu phi, which is the second derivative of the potential, and is absent if we treat gravitational field to be uniform within the box. Particularly, this effect will be vanishing. There will be no such effect if I take this very big box in the interstellar space, put a rocket on it, and carry it with acceleration a equal to g, and drop these balls. They will not come close to each other as they reach the floor. So this is the way to distinguish real gravity from the going to the accelerating frame. Okay, so the change in the separation between the trajectories of the two nearby particles, therefore, will be the probe of genuine gravitational effects due to space-time curvature. So in relativity, trajectories of free particles are nothing but geodesics, and therefore the acceleration of the aviation vector between two nearby geodesics should contain information about the curvature of space-time. I hope that this part is clear, because now I am going to first do a Newtonian calculation to show what happens in such a scenario, how to calculate the separation vector and how to calculate the acceleration of the separation vector. So I am talking about the geodesics, and I am also talking about two different a bunch of geodesics, not two different geodesics, bunch of geodesics. We consider a one parameter family of particle trajectories x alpha ts, where alpha basically it's not necessarily one parameter, it's basically two parameters. It's a multi-parameter family of trajectories where we have two parameters, t and s. I will explain what they represent. T represents standard Newtonian time, and S represents, or S basically labels different geodesics. I have plenty of them, different geodesics in the bunch, and alpha can take values 1, 2, 3, that is, they are spatial indices. So I can define the separation vector n alpha. I can also define the tangent to this, and this is my S, this is my S plus delta S, this is my S minus delta S. So as I move in this direction, S changes, and as I move in this direction, T changes. Okay, these are the two parameters. So if we take two nearby trajectories, think of these balls that I have dropped in the lift, and we consider two nearby trajectories, say S and S plus delta S. their separation vector will be denoted by n alpha of t equal to del x alpha ts del s. So this is the definition of the separation vector that we are going to use. And we also should know that if we want to compare between two nearby geodesics, that means if we actually say that what is x alpha t s plus delta s, I can do an expansion in Taylor series plus del x alpha del s. X alpha is a parameterized by t and s, delta s, and then there will be higher order terms in delta s square. And I will call this first term, this thing as n alpha t delta s plus order delta s square. Now I take this definition. And I want to ask the question, that what is the acceleration of this separation vector? That means as I move along these trajectories or fall, then how fast these trajectories are closing on in each other, or how fast these trajectories are diverging away from each other. So I need to basically look at this vector's acceleration. That means I need to calculate what is this quantity d2 n alpha dt squared. So that means I need to calculate del 2 del t2 del x alpha del s, because del x alpha del s is nothing but by definition n alpha. So this is because this is partial derivative, I can interchange the s and t, and I will first operate this on this x alpha, and I know that this del 2 x alpha del t square is nothing but gradient of phi, because del 2 x alpha del t square is the true Newtonian acceleration. This term is the true Newtonian acceleration, and this is same as minus del phi del x, which is the gravitational acceleration. So this will therefore be written as del x beta del s del x beta using the chain rule minus del phi del x alpha, or this is nothing but, because this by definition this object is the separation vector n beta, I will write it as minus n beta del 2 phi del x alpha del x beta. So we have just now seen that d2 n alpha dt squared is minus n beta del 2 phi del x alpha del x beta. So what does this say? This is known as the tidal tensor. And this is basically what is known as the tidal effect. So this is the gradient of the force. You can think of this as the gradient of the force. So the acceleration of the separation vector is proportional to the second derivative of the gravitational potential. That is clear from this expression, while the gravitational force is proportional to the first derivative of the Newtonian potential. So suppose the particle moves in a gravitational field of a point mass m. We have a point mass m, therefore I know what is capital phi? Capital phi is minus capital GM by small r. What is r? R is square root x beta x beta. We are in 3 space dimension, purely Newtonian calculation. You do this calculation, you can see how this potential and how the derivative of the potential gives us the tidal effect and gives us the curvature information. Del phi del r del x alpha, and therefore this is nothing but gm by r square del alpha r. So this is gm by r square del alpha. You can write it as x beta to the power half. And if you actually do this simple calculation, I am writing the the final result, gm by r cube x alpha. So now if you calculate del beta, if you calculate del beta del alpha of phi, after a few steps of algebra, I am not showing these steps. I will share the notes where you will find the steps, but I would suggest that you please go through the steps by yourselves. This is simple Newtonian calculation. All of you should be able to do it. Delta alpha beta by r cube minus 3x beta r to the power 5 x alpha. So in principle, n double dot alpha, which is d2 n alpha dt squared, is nothing but minus gm by r cube delta alpha beta minus 3 r alpha r beta n beta, and this r alpha is defined as x alpha by r, where this is true. So you can clearly see that the acceleration goes as 1 by r cube, and this is exactly similar to what you will see if what happens when tides happen on the surface of the earth. So the tidal effects are the most important gravitational effects that one actually uses to separate the effect of gravity from acceleration. Because I told at the very first class that it is very easy to actually negate the effect of gravity by going to an accelerated frame. So then the immediate question is, how can we distinguish the effect of gravity? This is the way that one uses to find out what is the effect of gravity. So let me stop here. Tomorrow I am going to utilize these definitions, these ideas that we have calculated in Newtonian case. Tomorrow I am going to calculate it in case of GR. I will see how, and this whole thing tomorrow I will start with geodesic deviation. This whole thing is known as geodesic deviation, and we will see that because of this geodesic deviation, it will actually incorporate the Riemann curvature tensor that we have introduced in the previous class, and that Bhaswati has discussed all its properties. And noticeably, Riemann curvature tensor r mu nu alpha beta, it contains gamma, and it also contains derivative of gamma. Now gamma, as I said, I mean, it's not gamma, it's product of gamma and then derivative of gamma. Gamma alone cannot actually separate the effect of curvature from acceleration, but derivative of gamma, if it is non-zero, that immediately tells you that there is curvature. The effect of gravity cannot be simply hidden away by going to a accelerated frame if there is non-zero gamma. Okay, so that we are going to see tomorrow, how this whole Newtonian calculation generalizes in case of general theory of relativity calculations. And from there onwards, we will try to arrive at, we will try to discuss the equation of motion in case of GR. That means essentially the target is, I do not know how far I will be able to go. The target is to basically use a variational principle to arrive at the Einstein's equation. Okay. Okay, so I stop here. So yeah, if there are any questions, why take negative sign in inertial force? No, I did not take negative sign in the inertial force. It is coming naturally because I just changed the side of that thing. You look at it. So I just changed. I took this equation, I multiplied with m, both terms, and then I took this on the right hand side, and that is why this negative sign came. Nothing else. There is no other reason behind this. So yeah, anything else? Any comments, suggestions? Okay, if not, then let us stop for today. We will meet tomorrow then.
Yeah. Okay.
Okay, thank you very much.
Yeah.
So I will stop sharing the screen. Thank you.
Yeah. Thank you. Thank you, Professor San. Participants, let us take some lunch break. Then we shall again meet for the tutorial session.